start. Are you ready?
Yes.
Okay, cool. Hello, good morning, good afternoon, and good evening. Welcome again to this World River and Delta series, Source to Think webinar series. Today, Dr. Brandee Carlson will give us a talk about the Yellow River Delta. Before I introduce Brandee, I would like to mention this coming Friday, and Bernard Poiker Ehrenbrick from Woods Hole, he will come here to talk about the Mississippi River in organic water chemistry. And as we all know, Bernard is leading the global river observation, the river basin study across the globe, as you can see here. I guess he will talk a little bit and also specifically focus on the Mississippi River water chemistry, And also Brandee here, as you can see here, she got her PhD from Rice University, and just May 2020 is just a year ago roughly. She currently postdoc with Steve Goodbread, our friend, in Vanderbilt, but on her way transition to University of Colorado border with our friend, colleague, Irina Overin, and over there, and will stay there for 1 year. She actually has already got an offer, a tenure track assistant professor, University of Houston, starting 2022. So that's very great. That's here you can see the picture, and Brandee traveled multiple times to China and working with our friend in Ocean University and other institutes on the Yellow River Delta. So I think here I will give the floor to Brandee. Now you can share your screen. So we're looking forward to your talk.
All right, thanks, Paul. Is this showing the correct view?
Yes.
All right, great, thanks. And yeah, as Paul mentioned, this is all of the work in this talk is in collaboration with colleagues at Rice University and OUC, Boston College, and others. So big thanks to all of the colleagues that were contributors to this work. Okay, so this is a source to sink seminar series. So I thought we should go ahead and locate ourselves for this talk. This is not a source to sink talk. Instead, we are focusing kind of on this smaller component of the framework. So you are here in this space where sediment is transported and sequestered. Specifically in this talk, we're going to think about how sediment is archived into the stratigraphic record along deltaic coastlines. And again, as Paul mentioned, we're going to be doing that by focusing on the Yellow River Delta in China, which thanks to the rapid dynamics of the Yellow River Delta, land is constantly built and destroyed on easily observable timescales. So in this talk, we'll explore the evolution geomorphically of abandoned delta lobes and distributary channels. And we'll use insights from this system to apply to kind of deltas globally, but we'll kind of explicitly focus on the delta system in our own backyard that we're quite familiar with. So the Mississippi River Delta, which like most deltas is home to many people. It faces reduced sediment supply, enhanced subsidence due to subsurface fluid extraction, reduced sediment supply to the delta due to the levying of rivers, and is impacted by sea level rise. So for the Mississippi, this has resulted in incredible land loss. And for the picture shown in the background of this slide, this would be projected land loss into 2050 at current rates. So the Mississippi, though, historically through avulsion, has built and destroyed hundreds of square kilometers of land on century-long timescales. So for the Mississippi, every 1,000 years, wherever the active river is located, it's building land and then abandoning it. And upon abandonment, that land can be reworked by tides and waves. So while the system is close to home, the system, it's also operating on a time scale that's kind of long to observe. So for this reason, in our field, we've historically been able to use the stratigraphic record as another way to kind of view a compilation of these events of avulsions that build stratigraphy. So here I'm just showing an example of an ancient delta lobe. So where at the base here we can see kind of this distributary channel body that's been built over kind of pro-delta plain material. Basically at the top of this sequence, we have abandoned delta plain. So this is kind of showing kind of what we think of in the stratigraphic record as this entire lobe building event that's been captured. So by looking at modern systems, we not only have value thinking about kind of societal impacts, but also it helps us interpret the stratigraphic record. And in turn, of course, the stratigraphic record can help us learn more about modern systems. So throughout the talk, I'm going to kind of be making these linkages to answer big motivating questions about what controls the evolution of river deltas and coastline geomorphology, and how is stratigraphy developed in modern fluvial deltaic systems. We'll do this by coupling field measurements and physical models. We'll look at time and space scales that can range basically seconds to thousands of years, centimeters to tens of kilometers. And again, we'll kind of be walking this line between modern systems and the construction of stratigraphy. So in the background, faintly, of this slide is again that picture that we looked at of the Mississippi River Delta and all of its previous delta lobes. Again, this is avulsing over long time scales. So for the rest of the talk, we're going to pivot to the Yellow River Delta, where these processes happen much faster. So here's the Yellow River. It's shown by the blue line. Its drainage basin is outlined in brown. The headwaters are in the Tibetan Plateau. The suspended sediment concentration in the headwaters have been reported up to 0.6 grams per liter. So while this picture of the headwaters looks fairly blue, it's actually still pretty sediment laden in its headwaters. As the Yellow River traverses through its mid-reaches, it passes through the West Plateau, which is a deposit of fine sediment. It's very fine silt and sand. So here the river picks up a lot of sediment to earn its name of the Yellow River. So the lower Yellow River is extremely sediment laden. We've measured suspended sediment concentrations of up to 30 grams per liter. So historically, this river has been able to deliver 1 billion tons of sediment per year to its receiving basin, with essentially a trickle of water. So this high suspended sediment concentration drives rapid delta dynamics. This is a schematic of the current and historical channel pathways of the Yellow River Delta. So blue is showing the modern river configuration, and each of these black lines on the schematic is showing an abandoned channel pathway. And these are all dated here on the right-hand side. So historically, the river has avulsed on these decadal timescales, essentially littering the delta plain with abandoned channels. we're fortunate with this system that we can look at kind of several recently abandoned channels. So basically since 1976, both diversions and natural avulsions have occurred in this area outlined by the red box. So we're now going to zoom into this area and watch basically a reel of Landsat images that capture the most recent dynamics. Okay, so this video starts in 1984. So we have a lobe building out into the Bohai Sea. It's building out at about a kilometer per year seaward. In 1996, an engineered diversion relocated flow to the northeast. The abandoned delta lobe is retreating rapidly. The shoreline's retreating rapidly. Meanwhile, the new lobe is building out at a comparable rate of about a kilometer per year. However, while it's building, we kind of start to see these crevasses over the north bank. And this occurs over the case of multiple years until a small natural avulsion relocates flow kind of up to the north. So we kind of end up with these multiple examples of one, this really kind of abrupt diversion of sediment and water due to an engineered diversion, and this kind of slower natural avulsion that takes several years, and this channel retains some amount of connection, surface water connection to the active channel today. Okay, so for this talk, we're going to have two objectives. The first is to look at how abandoned deltaic distributary channels are filled by marine sourced sediment. The second objective, which will focus on the controls of stability of shorelines of abandoned deltaic lobes. So we're going to look at this first objective using the lobe abandoned by diversion. So this is the Chingshui-Guo lobe. This is on the left. We have a Landsat image. If we look at it in plan form, we can see the old levees of the abandoned channel, and between these levees, you see it's kind of big, muddy, flat. The picture on the right, I took standing right here in 2015, looking off into the Bohai Sea. So let's zoom into that picture. Okay, so now we can see the relief that exists from the antecedent levees. These levees are vegetated. The levees are about 600 meters apart here. And in between the levees, we have this mud flat and a tidal channel. So we can make some kind of observations that it appears that this abandoned channel is filled by mud and occupied by the subordinate tide channel. So from this, we can make a hypothesis that perhaps the mechanism for sediment deposited in this abandoned channel is that sediment-laden water can be conveyed by the tidal channel and deposit within the abandoned channel, building a mud flat. And we can test this hypothesis by documenting both the abandoned channel stratigraphy and looking at the flow of sediment and water here. So we're going to collect data. We're going to collect field data, kind of build a simple morphodynamic model to inform these channel infilling processes. But first, just to build our intuition a little bit more, let me get off of my laser pointer. We're going to view a video that was taken from a game camera that we deployed on the mud flat. So it's facing the tidal channel and the abandoned channel levees. We have this dowel network set up in front of the camera. So the dowel closest to us has increments denoting like 5 centimeter increments. Farther out, we have a dowel showing 20 centimeter increments, you can kind of see the footprints from where we set up this dowel network. What we're seeing in this video is that every day there are 2 high tides and 2 low tides, where one high tide is higher than the other, one low tide is lower than the other. This is a mixed semi-diurnal system. By the end of this video, we can see that our footprints from where we set up this dowel network has been erased. So it's kind of a testament to the fact that certainly at least tides are reworking and most likely depositing sediment in this flat. And also just this is kind of a nice visual to look at for how things might be working, but we've also heavily deployed instruments across the site. So we'll take a look at that data next in the talk. Okay, so now that we've kind of all seen what this tidal inundation looks like, we can build a basic model. And the way that we're going to build this model is we're going to say, we have our old abandoned channel levees, and in between those levees, we have a tidal channel and a mud flat. So at low tide, water and sediment is kind of contained in this tidal channel. At high tide, sediment is suspended, and some of that sediment is suspended in elevations above the surrounding mud flat. But we can build a concentration profile for what the sediment might look like in the tidal channel by considering properties including water depth and properties about grain size, including settling velocity and also velocity, so that we can get velocity profile so that we can get shear stress. For sediment that's present at elevations in the water column that exceed the surrounding mud flat, if there's a component of velocity that's transverse to tidal channel, we can predict the distance over which that sediment might settle. So we can very simply calculate that as an advection length scale, which is again dependent on that transverse flow velocity and the settling velocity of the particle. So we have kind of a list of parameters that we can go out and measure in the field. And these parameters will basically help us build this simple model that we've generated. So yeah, let's take a look at some of the field data that we collected. We collected field data over 2 seasons. So in the summer, so this is our research vessel from the summer. So we're sitting in the tidal channel. You can see the mud flat off in the distance. This is our crew. We have instruments that are like constantly monitoring. We also are deploying instruments kind of off the boat during anchor station times. We also conducted surveys during the winter, and the idea here is that basically big storms happen due to the East Asian monsoon during the winter, and we know that this can churn up a lot of sediment in the Bohai Sea, and we were interested in capturing those impacts. So we went out during the winter of 2018, and we captured data during 3 different storms. And as you can see here, it was a cold mission. All right, so let's start looking at that data. Okay, so this is to the right, we have a bathymetric and topographic map of this field site. We're going to focus on instruments that were located along this transect from A to A prime, where along this transect we had pressure transducers giving us information about water depth. We had acoustic Doppler velocimeters, so ADVs that were helping us get velocity data. We had OBSs to help us calculate suspended sediment concentrations, and tilt current meters to also as another way to get velocity. So first we'll look at the water depth records. During the summer, we saw that we had this really kind of, again, nice spring neap signature. So we have these also mixed semi-diurnal tides. During the winter storms, these big winter storms that we were able to measure totally obscured this signal. So every time we had a big storm, we kind of had these high water depth events. So this helped us to constrain our model parameter for water depth. For velocity, we again can see kind of this nice mixed semi-diurnal tide signature as well as our spring neap. We have a maximum velocity of up to 1 meter per second, and that's associated with the ebb tide. During the winter, again, these big storms are kind of obscuring our velocity. So we have these kind of big excursions associated with storms. And again, this is helping us constrain our model parameter for water velocity. For our suspended sediment records, we find that the peaks in suspended sediment concentration are occurring in association with our spring tides, but also that we're seeing small peaks with the max flood and ebb. And during our winter campaign, we had a really interesting signal where we just observed overall very, very high suspended sediment concentrations at this site. And during storms, the instrument was zeroing out. So we at least think that suspended sediment concentrations were exceeding the instrument max of 1,200 milligrams per liter. Channel bed grain size. We found during the summer that we had a median grain size of 80 microns. And during the winter, we saw that there was a bit of fining on the tidal channel bed. So a median grain size of about 60 microns. And these data are going to help us constrain our model parameter for settling velocity. Okay, so now we've taken kind of a quick look at some of the field data that we collected that can inform this model. So we're going to go ahead and look at some results. First, we'll start with the concentration profile. Okay, so when we build concentration profiles using the range of observed shear stresses, what we found, and a range of observed channel bed grain size, we kind of build these concentration profiles that range here, where suspended sediment concentrations on the X, and we have a normalized water depth in Y. So each of these colors, this red is representing kind of a low shear stress condition, yellows indicating high. We have also measured suspended sediment concentrations for near bottom and at the top of the water column. So, we find that our model for concentration does a fine job of predicting the observed kind of range of suspended sediment concentrations. So we'll move forward with the next step of the model. And for this, basically, we will kind of take all of the sediment that's present in the top of the water column. So here I'm showing this red box saying, okay, we're going to take this piece of the water column and all of the sediment in it and advect it towards the mud flat and allow it to settle using our advection length model. Okay, so if we do this for all the sediment present at the top of the water column and allow it to settle over a range of observed slack tide conditions, we predict this kind of range in sediment size distribution shown by the black lines and this kind of darker gray slug. Now, if we take those grain size distributions and compare it, so those are the predicted, and if we compare those to what we observe on the flat, we kind of, that's shown here by this kind of lighter gray slug. So we see there's pretty significant overlap in grain size distribution. So we think the model, we're doing a fine job of modeling the predicted range of observed grain sizes. So when we took this model like one step further and said, okay, let's assume that this is how, that this model can kind of represent how sediment is being advected towards the mudflat over the entire time that this channel has been abandoned. If we kind of take, if we take those concentration values and allow all the sediment to deposit over time, we would predict that we would have an aggregation rate of between 0.7 and 2.2 centimeters per year. Well, we can test how good that prediction is by looking at the stratigraphy of the abandoned channel. So we did this using 17 6-meter long vibrochores and 45 trenches. So these are those locations here. What we found is that there's this kind of top finer layer of sediment that's sitting atop a coarser package of sediment, where this coarser package of sediment, if we look at those grain size distributions and statistically compare them to the current active channel bed, they're somewhat like indistinguishable. They are indistinguishable. And so we interpret this coarser package to be the abandoned channel bed, and that all of the fine sediment that's sitting atop this coarser package is sediment kind of delivered by tides. We look at the average thickness of that fine sediment and consider the time of abandonment, we would predict that sediment is accreting at a rate of about 2.5 centimeters per year on average. So that's a little bit higher than what our model predicted. So why might this be? Well, this mudflat is building in an old abandoned channel, and that channel had antecedent channel topography. So it had old bars representing antecedent highs and a thaw leg representing an antecedent low, right? So we went back and kind of looked at satellite images of low discharge conditions for this channel. And we overlaid our core and trench data and tried to see if there was any relationship between placement between old bars or proximity to the thaw leg and mudflat thickness. So what we found is that there was a higher range in mudflat thickness in close proximity to the thaw leg. So, we think that this supports the idea that, antecedent topography is playing a first order control on overall mudflat thickness here. So for this first half of the talk, to wrap this part up, we found that for an abandoned channel, abandoned by diversion, the primary mechanism for sediment delivery is tidal. At present, this abandoned channel is still kind of an underfilled topographic flow. It's still actively filling. And antecedent topography likely is controlling that mudflat thickness in the channel. So for the second part of the talk, we'll look at comparisons between these old abandoned shorelines and look at their stability from engineered diversions versus kind of this natural avulsion. So deltas, again, to harken back to Mississippi, we know that they're at high risk, and because they're at high risk, we want to mitigate land loss. And a proposal to kind of combat some of this land loss is to divert water and sediment from the active channel to the surrounding regions to nourish drowning wetlands. So, so basically the idea for these structures is that basically at a local engineered structure at the point of diversion, delta building processes will take over kind of delivering sediment, and natural delta building processes can take over from there. And for the Mississippi River, this has actually happened in the past. So for an example of that is like Cupid's Gap. Also, there's regular flow distribution from the main stem channel through the Atchafalaya at the old river control structure. And so while these systems do provide really valuable examples of how land building can occur for the Mississippi, the Yellow River Delta is still this like wonderful example of looking at land decay processes, which we're going to do in hopes of trying to understand how we can optimize kind of subaerial sustainability of delta lobes in the face of reduced sediment supply. Okay, so now what we're going to be looking at is shoreline positions through time for 3 abandoned delta lobes. So first, this figure is showing the shoreline of the Yellow River Delta in 2018. If we go back to 1976, we can see the shoreline traced in yellow. We used Landsat images to basically extract shoreline position through time, which is what's plotted here on the right. And what we find is following this diversion, which basically cut off all upstream sediment and water, we see shoreline retreat occurring at a rate that exceeds 400 meters per year, but eventually does kind of reduce over time. So following this 1976 diversion, flow was relocated down here to south for the Chingshui lobe, which we just focused on. So flow was located here until 1996. And following that diversion, again, we see a shoreline retreat rate that exceeds 400 meters per year. So, so following that diversion, the Qingba lobe was built, and a small natural avulsion relocated kind of the lower 10 kilometers of that channel to the north. So when this happened, we found that the shoreline retreated at a rate of about 90 meters per year. So there's pretty significant discrepancies in these retreat rates. And we know that shoreline retreat for deltas is controlled by many different things, including sea level change, wave climate, sediment supply, vegetation, inherited morphology, and subsidence. So we're going to take this observation that there are kind of big disparities in these retreat rates to the tune of, this the avulsion shoreline is retreating at a rate that's about 4 times slower than the engineered diversions. We're going to kind of investigate if any of these controlling factors may be responsible. So we'll test here in this talk, at least, we'll test controls from wave-driven sediment transport, vegetation, inherited morphology, and freshwater and sediment supply. And to do this, we'll use a model for wave-driven sediment transport. We'll evaluate vegetation coverage, and we'll look at the inherited morphology with remote sensing. Okay, so hypothesis 1 that we'll test is that waves control differences in shoreline retreat weights. We'll do this using Shoreline S, which is simply a coastline model that's able to describe large coastal transformations due to gradients in a longshore sediment transport. So we will inform this. So this is a model written by Donna Rolbank. We can use field data to kind of help constrain certain parameters of this model. So for instance, our colleagues at Boston College collected data on, they collected wave data. So we used this to help inform the model, as well as kind of our historical shoreline configurations. So our results from this model, when we looked at predicted shoreline retreat rate, are shown here. I'm going to show them as cumulative distribution functions so that we can kind of look at the range of behavior. So first we have Dialco, so this globe orientation to the north. We subjected it to kind of these fair weather waves and storm wave conditions. So this kind of bi-directional wave climate. And what we found is that for Dialco, it's predicted to exhibit some retreat, but interestingly, it looks like a little bit less retreat in storm conditions and fair weather conditions. For Qingxuiguo, we found that that fair weather waves kind of generate this kind of tightly distributed near zero daily change, whereas storm waves have a quite variable response ranging from shoreline retreat to progradation. And for Qingba, we observe that fair weather storms don't really do much to alter the shoreline position. However, storms certainly do. So the orientation of the slope relative to the storm wave climate is predicted to have pretty significant shoreline retreat. But interestingly, kind of all of these predictions don't match our observations. In fact, they're nearly opposite. So, because of this, we're not really convinced that, sediment transport, because of lobe orientation relative to the wave climate, is really responsible for some of these discrepancies and retreat rates that we see. So we wanted to investigate kind of other things that are not accounted for in this really basic shoreline evolution model. So things that are not included are kind of at least in some regards, included on this list. So vegetation, inherited morphology, and freshwater and sediment supply. So we're going to now kind of investigate the rest of these throughout the talk. So now we'll test the hypothesis that vegetation may be controlling differences in shoreline retreat rates. This is possible potentially because plants on deltas can enhance sedimentation through reducing turbulence and flow velocity. They can inhibit the remobilization of sediment, and they can mitigate wave-driven alongshore sediment transport. So first, we're just going to try to quantify vegetation distribution using remote sensing. So along the shorelines of each of these lobes, we first, just in field observation, saw that kind of along the shoreline of Qingba, there's these kind of nice marsh grasses, Spartina, whereas, for example, along Qingxuiguo, the engineered diversion, it's just this kind of barren mudflat. We can try to quantify these differences in vegetation using the normalized difference vegetation index, which is a proxy for live green vegetation. So for both of the engineered diversions near the shoreline, we see 0 or near 0 values for NDVI. So this kind of supports our field observations that these are barren. For Qinghua, we see an increasing NDVI value, and which is interesting because it continues to increase even after the avulsion. So this kind of supports the idea that not only that there is more vegetation, but that it looks like vegetation may be increasing in density through time. So our result here is that vegetation density certainly does kind of vary between these abandoned delta lobes. And to look into that a little bit more, like why this might be, like why does Qinghua potentially have so much more vegetation? We can, first of all, see here with the active channel, it's connected to the abandoned Qinghua channel by this tide channel. We also have big tidal channels that are conveying water from the Bohai Sea. If we look at vegetation species on or within this abandoned channel, kind of close to the active channel, we see a lot of Phragmites. So Phragmites will tolerate some salinity. They have a germination depth that is required to be less than 5 centimeters. So if we move downstream though, to where we start to see kind of Spartina as our dominant species, they will tolerate higher salinity and also larger germination depths. But that being said, the upper limit on germination depth is 45 centimeters. So this at least puts some limit perhaps on what topography may have been when this channel was abandoned, considering it was conducive to kind of vegetation colonizing it. So we think that this kind of, again, antecedent topography was probably in part responsible for allowing vegetation to colonize. Okay, so to return to our list, yes, we think that vegetation, at least there are discrepancies that could help us explain our shoreline retreat rates. So let's take a look further into this role of inherited morphology. So we have our kind of third hypothesis that maybe lobe elevation controls differences in shoreline retreat rates. And we kind of evaluated this by looking at topographic highs and lows prior to channel abandonment using remote sensing. And we did this using the modified normalized water difference index. So we basically took images of the abandoned channels at similar discharge conditions and looked at within each channel how much subaerial bar coverage was present. So for similar discharge conditions prior to abandonment, we found that less than 10% of the Qingshui-Guo, so this engineered diversion channel, was covered in subaerial bars. While for Qinghua, we found that kind of more than 30% of the channel was covered in bars. So we do see kind of a significant difference, suggesting that perhaps there was more high topography areas in Qinghua prior to abandonment. And if we zoom into these bars and kind of look at elevation surveys that we conducted during our fieldwork, so this was collected in 2016, we find that where the bars were, which again is demarcated by the red box, that even in present day, this is still a topographic high, and it actually corresponds pretty well to this kind of dashed line that's showing where elevations are super tidal. So we think that kind of this, again, this antecedent channel topography in modern day is still setting up some of the elevation differences that we see between these channels. So yes, we do see discrepancies in inherited channel morphology. So finally, let's take a quick look into the idea that perhaps fresh water and sediment supply is helping promote this vegetation that's controlling shoreline retreat rates. And to look at this, we can measure flow characteristics. So we did a lot of this in the first half of the talk, where we looked at kind of that marine delivery of sediment and water to this abandoned channel, abandoned by diversion. Again, there's no upstream component of sediment and water delivery to this channel. And we've measured salinity in this channel to be saline to hypersaline. Alternatively, in the Qingba channel, this naturally abandoned channel, again, we have this direct connection to the active channel, delivering fresh water and sediment. We have measured fairly low salinities, kind of in this upper reach. And as we traverse downstream, salinity increases as we approach the Bohai Sea. So we do have a big discrepancy in freshwater and sediment delivery that's reliant on this connection to the active channel. So yes, we do see a difference here. And kind of want to tie some of these pieces together by discussing, the role that ecogeomorphic feedbacks may be playing here when we're trying to understand shoreline retreat rates. So vegetation relies on elevation for wetting frequency and duration and salinity conditions. But once it's established, it can help promote sediment aggregation. So we think that these linkages between vegetation, freshwater and sediment supply, and inherited morphology are likely at least part of the reason that we observe kind of these slower retreat rates for the Qingba lobe compared to the engineered diversions. At least in our circumstance, we weren't able to kind of include lobe orientation relative to wave climate in this kind of overall model. So to conclude, following 2 engineered diversions and 1 natural avulsion, shoreline retreat rates vary vastly and likely reflect natural versus kind of human impacts on sediment and water supply to these receding lobes. Channel bed topography prior to abandonment, sediment supply, and vegetation density, we think are the primary controls on these retreat rates. And we also think it's an important feature, perhaps for future engineering endeavors, that this natural avulsion does maintain a tide channel that supplies fresh water and sediment to the lobe, facilitating vegetation growth, which may help buffer some of the shoreline retreat. And so with that, I'll take questions. And I guess if anyone has questions later on, please feel free to email me.
Brandee, thank you. Thank you so much for this wonderful talk. And because particularly, you are in Houston, and also Jeff also work on the Mississippi River. You talk about a little bit of comparison, because the Mississippi River Delta, have a big problem with subsidence. People talk about diverging all the time. Recent year, that the news always said Louisiana has a plan to punch a hole on the Mississippi levee to, cause that kind of, you show the small pictures. And nowhere like the Yellow River Delta have a natural experiment lab already have that kind of diversion many times. So the lessons learned from Yellow River Delta can apply somehow to the Mississippi River Delta. I think this is two wonderful delta can do a bunch of comparison. Maybe we should write a short communication or some report. And that should be wonderful, particularly the Qingba one. So I pay attention to the Qingba one, recent years. It's interesting you put vegetation as a factor in the equation. A couple months ago, Tom Quest talked about the marsh over the Mississippi River Delta. I think that will be very interesting. Of course, there's many other factors we can consider. So let's open the floor to the audience. Do you have any question? And you can unmute yourself directly, ask, or you can type your question in the chat room. And so Brandee said, great talk. And so, so anybody go ahead if you have any question.
Okay, Paul.
Jinping, go ahead.
Yeah, hi, Brandee, it's Jinping. Thank you for the good talk. I noticed you used quite a few very high resolution images from the satellite. I'm wondering, do you have to purchase them, or it can be downloaded somewhere freely? Could you?
Yeah, everything that I used was free data. So if you're interested in images after, I think 2016 is the earliest that we can get, Sentinel has really high resolution images that are beautiful. The only limitation is that the ones that we have access to for the Yellow River Delta are fairly recent. So Landsat certainly offers that longer archive.
Yeah.
Sentinel from 2016, right? Mainly.
Yeah.
The time-lapse photograph, I remember I saw that several years ago in Zhengzhou in a talk presented by
Michael Lam.
Yeah, Michael Lam. Yeah. I think you put a few more images into that series. It's beautiful. Okay, thank you very much.
Thanks.
So one thing, Brandee, maybe you can talk to Michael and they should redo that animation. They should put a year. If you look at there's no label show which year of that one. It's easy to redo that.
It has a very, very tiny label that should be redone so we can all see it. That's right. We should redo it.
Yeah. Can you go to your slide number 23 or 24? Show the tidal speed.
Sure.
23, 22, something like that. You can exit the full presentation mode and then go back to and choose the.
Oh, let's see.
You show the
so
screen. Can share the screen.
Yes. So is the tidal velocity that you were interested in?
Yeah. Can you presentation too small now? Yeah.
Can you see that?
No, this is the first page.
Oh gosh. Okay. I'm sorry. These are 23 and 24.
22.
22.
Go up. Yeah, this one. So, okay, good. Okay, that's nice. The next one, can you? Oh, up one. I forgot which one. Oh, this one. So the velocity here, there should be something wrong. It's not the meter, it should be centimeter or something.
Oh, yes, it should. That's a mislabel.
So it's just less than 1 meter per second somehow. Okay. Well, it's a great talk. There are many, I have many questions. I need to digest. I have a question maybe later. So let's see. And Michael, I saw you unmuting yourself. Yeah. Okay.
Yeah. So yeah, great talk and congratulations on the new job. Actually, looking at this slide, what you see is that during the summer, the peak velocities during the spring tides are not very different from the peak velocities in the winter. But you had much more sediment transport in the winter, right?
Yes.
Yeah. Why are you getting more sediment transport even though the velocities aren't very different?
So we think there's a pretty important role of import from offshore. So basically during the winter, there's kind of these big wave events that are churning up fine sediment. And we have evidence that that's transported to the tidal channel, not only through our concentration data, but also the tidal channel bed fines. So we think that kind of in the winter, we have this import of fine sediment that's resuspended by local currents. Yeah.
Okay, so those storms are also stirring up a lot more sediment, and yeah, I mean, isn't there a difference in the net onshore and offshore currents in the area in summer and winter?
Yes, but at least in this like local area, we think that what's happening, at least in the tidal channel, is that there's kind of a net import on the bed, but that kind of during fair weather conditions, local currents can resuspend that fine data. So it kind of ends up getting transported likely back to some degree back offshore.
Okay.
If I might just add, Mike, I have a master's student who's finishing up and is looking at basically the difference in wave climate, summer and winter on the Delta front. And it's all in the winter wave. We've got these huge wave events that come every couple of days and just charge the water column with sediment and essentially swamp the input into the abandoned channel. And then that gets reworked during non-winter.
Okay.
Yeah. That's very interesting. Okay.
So keep your eye out for a nice paper coming out by Michelle Mullane. And if I can also plug Lisa Kumpf, another master's student is finishing up, and she was responsible for the in-channel transport measurements.
Wow. Okay, that's great. That's great. Very, very interesting. So Brandee, in the Qingbao, so how much sediment still supply from offshore into the channel, or not much because the elevation a little bit higher? So that should be different from Qingshui-Gu, right? Qingshui-Gu, there are some coming in, right?
So we think for Qingshui-Gu, it looks like it's exclusively from the marine delivery. Yeah. For Qingba, we think it's a mix. So certainly kind of close to the Bohai Sea, there are big tidal channels that are conveying sediment. It builds kind of a little bit of kind of mudflat area, marshland area. Yeah, basically anything that's intertidal. Yeah.
Yeah. Another factor to consider is Qingbao still very close to the active river mouth. And I don't know, this may be another factor to slow down the ether retreat.
Absolutely.
So I think it's very interesting. It's a very good talk. And so anybody else? Anybody, I saw many Chinese colleague, any student, you even can ask your question in Chinese. We translate to English. Well, any? No. I think thank you, Brandee, and this is a great work. And so, which river, which system you were working on in your postdoc?
Well, I worked on. Well, I've looked at a lot of Steve Goodbread's data, his core data from the Ganges Brahmaputra. So I'm interested in getting more involved there. And with Irina at CU, we'll be working on a fjord system in Greenland. Yeah.
Cool. Okay, very nice. Let's see, Brenda, maybe you stay a little bit longer. Let's see, Irina is coming or not, so we can have a little bit, see. Okay, then other than that, thank you very much. I will stop the live streaming here. So.